All good? And then we'll go ahead and take a look at a few examples. Okay, first thing first. Okay, if you have not done so, okay, writing the program to generate the pattern and have another program or another part of the same program to filter and give you both a count and also the actual pattern, do it. Okay, it is extremely helpful for two reasons. One is when you're coding it, you already start to think about the problem a little bit. Okay, because especially when you code the filter part, if you code the filter part correctly, then you already know what the numbers are for. Okay, what kind of chances are we talking about? So that's the first reason. The second reason is if you code it and you code it correctly, then you know the correct answer for specific cases already. So at least you have a baseline to compare your theory against. Without that, it is extremely difficult to find out whether your theory is correct or not, even for specific cases. So if you haven't done it already, I would strongly recommend that you write a program to do at least the empirical part of this problem. Okay? All right. So given that we have done that, so we'll go ahead and look at a few specific cases. So when n is 10, which means we have a circle of 10 numbers, and r is also 10, which means we have a sequence of at least 10 numbers, or we have at least 10 numbers in sequence. When we only have 10 numbers, that's an easy case, right? Because you can only have so many ways to arrange numbers like that. So it would be like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And of course, there's also the other way around, which is 10, 9, 8, 7, 6, 5, 4, 2, 3, 2, 1, which is the opposite way. But that's really just symmetric. It's a rotational mirror image. And you just double it, okay? That's an easy one. But then you also have the rotations, because you can start with 10, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, which is a rotational shift of the original pattern. So if you think about it, then you have 10 ways to rotate, and then for each way, or for each rotational location, then you also have the counterclockwise way of counting. So you have basically 20, okay? So that's how we come up with the idea of, maybe we have 2 times n way of arranging these things. So in this case, we have 20 ways of assigning numbers in 10 slots in a circle that will have at least 10 numbers in sequence. Okay, that's an easy one. Okay, next one up is what if r equals to 9? Okay, so you think about n equals 10. Okay, n is still 10. R this time is 9. Okay. Okay, so that means we want to have. It's asking what are the chances that we have at least 9 numbers in a circle in sequence out of 10 possible numbers. Yep.
Wouldn't it be the same?
It would be the same, exactly. Because if 9 numbers are in sequence already, we only have 1 number left, right? So how do we know that number has to be in sequence as well?
There's nowhere else for it to be.
Sorry, go ahead.
There's nowhere else for it to be.
There's nowhere else for it to be. Okay? Yep, exactly. You can prove by contradiction and say that, okay, what if that number is actually out of sequence compared to the 2 numbers that are at the ends, and you will find that it's not possible. Okay? All right, so this ends up with exactly the same thing, which means the frequency is also just 2 times n. So if you actually wrote the program, if you actually write the program, because many of you already wrote the program to do all these cases, it will give you exactly 20. Okay, when you say n is 10, it will give you exactly 20, and it will give you all the patterns, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, and so on. So it will give you all the patterns. By looking at the patterns, you would know, okay, I know how the patterns, or I know how I have 20 cases. So it would give you ideas, it would give you some clues of how to generalize the pattern into numbers. So the next one up is 8. Okay, so n is 10 and r is 8. All right. So this one, we worked on this one actually after this class, because some people are also in the assembly programming class, and we worked on this a little bit. Okay, so with this one, the question is, the important part is asking, what are the chances that we have a sequence of at least 8? So a sequence of 9, which is a sequence of 10, will also meet this requirement, okay? So in order to figure out the pattern, you want to know, okay, what are the number of ways to assign numbers that will end up with a sequence of exactly 8, 8 numbers in the sequence, because 9 and 10 are already accounted for. I'm not interested in those. I just want to know exactly 8 this time. Okay, so that becomes a slightly different problem. Okay, so we focus on number of ways to assign numbers in a circle of 10 slots to end up with exactly 8 numbers in a sequence, okay? Which is not what the homework assignment is asking, but thinking about this one will help you get to the answer that I'm asking in the homework assignment. So let's focus on this one. So quite obviously, we have 1, 2, 3, 4, 5, 6, 7, 8, okay? 8 numbers in sequence. But then the last 2, I really don't get a choice, do we? Because if I have a 9 here, it's going to complete the sequence. So I must have a 10 here and a 9 here. That's one way. But this time, the 1, there's nothing that can wrap around to deal with the 1, because 1 is already at an end, okay? What about the other option? You can start with 2, 3, 4, 5, 6, 7, 8, 9, and then you cannot have a sequence anymore, so you can put a 1 here and a 10 over here. Is that making any sense? That's the longest sequence is only 8 numbers in both cases. Are we doing okay so far? Can I start with a 3 and still make it unique and not a rotational copy of something else? Nope, not possible, because if you start with 3, you would end up with, you cannot have a sequence, okay? Because if you start with a 3 and not counting the wrapping around, 3 can only count up to 10, which is only 7. So you cannot have a sequence of 8. Is that the case? Okay, all right. All right. No, I think I got it wrong. You can start with a 3. I take it back. 3, 4, 6, 5, 6, 7, 8, 9, 10. And then you cannot have, then you can have any number after 10.
You can only have 2 numbers. You have to do 1 or 2. 2 and then 1, right?
Oh, 2 and 1 here. Yeah, but technically the restriction is because of the 1 and not because of the 2. You can choose any number after 10. You cannot choose any number as the last one because it wraps around to the 3. Okay? So there are 3 particular patterns here. Each one has 10 rotational positions, and also you can do it backwards as well. Yep.
We don't understand the 3 portion things. Like,
The what?
So for exactly 8, can't you start with like any number? Like
But then it will be a rotational copy of one of these 3.
But isn't it okay just to list the first one and then say that there's n of those rotational copies?
Then you have, well, okay, if you look at rotational copies, then you have to make sure that you don't end up with duplicate copies because of rotating.
Because the way I see it, isn't the second and the third, aren't they rotational copies?
No, they are not. They should not be. You are looking at the second one and the third one. They are not rotational copies because with the second one, we have a 3 following a 2. With this one, we have a 1 following the 2. So they're not, they're distinct. They're not, you cannot rotate one and end up with the other one. So these 3 cannot be duplicates. Even if you rotate the whole thing, you do not end up with these patterns. Okay. So now we have 3 of these, and then each one has 10 rotational positions, and then reverse counting is the other, it will double it. So now we end up with what? 60. Are we, yep.
So why are we limited to 3? Why can't we create one that starts with 4?
Because if you start with a 4, okay, so let's go ahead and start with a 4, and we want to end up with a sequence of 8, right? Exactly 8 numbers in sequence. So 4, 5, 6, 7, 8, 9, 10 is as far as I can go, and this is only 7 numbers. So that means in order to end up with a sequence of 8, I will need to put a 3 here. If I put a 3 here, I only get one way to assign the numbers to these 2 empty slots. Because I cannot have a 2, here, because that will make it a complete sequence. So the 2 has to end up here, which also means the 1 has no choice but to go here. But now it is a rotational copy of the one right before it. Do you see what I mean? So I just want to make sure that I come up with only the unique ones and then use rotations to deal with all the possible configurations coming from the same, I guess, root or core pattern. Is that okay? Yep.
Can you have one in there that goes from 3 to 8 and then starts? Never mind.
Okay. So now we have 3 core patterns. Each core pattern can go in both directions, which is times 2. And then for each one of those, we can also rotate it 10 times. And each time we rotate it is a different pattern. So we end up with 60. We end up with 60 patterns that have exactly 8 numbers in sequence. Okay? So when the question is, what is the number of ways to assign numbers? So we have at least 8 numbers in sequence. It's not 60, it is 60 plus whatever we have with the other ones. So it'll be 80. Okay. So
Sorry, how you got the 3 times 2 times 10?
because these 3 are they are unique patterns. Even if you count counterclockwise versus clockwise, they cannot generate each other. If you count rotation, they cannot generate each other either. So that means we have 3 core patterns. For each core pattern, you can rotate the entire pattern, and each position you rotate becomes a new outcome. So that's why that's why we do the times 10. And then counting clockwise is different from counting counterclockwise.
That's the times
So
2.
that's the times 2.
Okay.
Yep.
But rotated would be the same number, so.
No, it would count the different outcomes.
No, like, let's pick one of those 3, and then we rotate it, it will have the same number, right, the same sequence. So there's
No, these 3 are unique.
No, what I mean is just pick one of the 3,
Yeah.
and then put it in the circle.
Yeah.
Right? And then rotate it. That's exactly the same number before rotation. So there's no point of turning it 10 times, right?
But those are different outcomes. Okay. Okay, I think we're getting confused about combination versus permutation. Okay. Let's think about a smaller case because I don't have to write as much. Okay. So you have a circle of 6 slots. Okay, 6 seats here. We'll number the seats A, B, C, D, E, F. A, B, C, D, E, F. Right? So the question is, how can I assign numbers to the seats so that we have at least a sequence of 3, a sequence of 4, and so on? That's the question. 1, 2, 3, 5, 6, 4. Oops. Okay, the felt tip has retracted. What happened to all those markers? I have one that I stole from 126. So this one has 1, 2, 3,
But
5,
that won't make it
6,
to the
4.
video.
Hmm?
That won't make it to the video.
It'll be beeped out. But this is a unique one compared to the next one, which is 1, 2, 3, 5, 6, 4. These 2 are different outcomes. Because when we look at omega, which is the set of all possible outcomes, This is the permutation. This one, or the cardinality, is 6 factorial, which is basically counting these two as unique outcomes. So that's why rotation is important.
Yeah, but let's stay within the inner circle. The 1, 2, 3, 5, 6, 4.
Uh-huh.
If we rotate it, that's actually the same number as the one. So let's start with A. 1, 2, 3, 5, 6, 4. Now let's rotate it to the right, or clockwise. We'll have 4, 1, 2, 3, 5, 6.
Yeah, which
That's
is what
exact
the
same
orange number is.
Yeah, but that's the exact same number.
Well, we only have 6 numbers all the time. We only got 6 numbers. It's the permutation that is important. It's not just the combination. If you count just combination, then it doesn't matter how you write the numbers. It's considered the same 6 numbers anyway. Okay, think about this. 6 choose 6 is by definition 1. There's only one way you can choose 6 things out of 6 things when you only consider combination, where ordering is not important. So but on the other hand, when you have the permutation, if you get 6 things out of 6 things where the ordering is important, this is 6 factorial, which is 120. And in this case, ordering is important. Who starts does matter. Whether you start with a 1 or you start with a 4, even though the sequence is the same, who starts the entire sequence is important. Yep.
So it's like in your assignment, you said that it's people drawing cards.
Yeah.
So if those cards are values of money, then it's easier to see that the different orientations are definitely important because you get a different amount of money.
Exactly. That's a good way to put it. That is a good way to put it. So are we okay with that concept where ordering is important? So if ordering is important within the same assignment, it is also important when you compare one assignment to the next assignment because ordering is important. Okay? All right, so we are going to move down one more where n is still 10 and r is 7 in this case. Okay? So in this case, we are not concerned about sequences of exactly 8 numbers or sequences of exactly 10 numbers because we got those numbers already. So this time we want to focus on numbers of ways to assign numbers in a circle of 10 slots to end up with exactly 7 numbers in a sequence. Okay? So 8, 9, 10 are all done. I'm only now focusing on exactly 7 numbers in a sequence. Okay? So you can use the same method as before and say, okay, we got the easy one right here. 1, 2, 3, 4, 5, 6, 7 is a sequence of exactly 7 numbers. Of the 3 remaining numbers, I just have to make sure they're not a sequence. They do not continue this sequence in any way. That's all I know. That's all I need. Because once you have used up 7 numbers already, whatever is remaining cannot be another sequence of 7 numbers. So all you have to do is to make sure it does not continue this particular sequence. Well, the only number that really has the only spot but there are 2 spots that are of significance. The 1 slot right after the 7 is significant because of the 3 numbers remaining, only 1 will continue the sequence. The other 2 will not continue the sequence. So in this case, I can pick a 9 after this. And the last one is not important because nothing can continue the sequence wrapping around because no one can actually go before a 1. So out of the remaining numbers, which is an 8 and a 10, the ordering of those 2 is not important. So I have a 10 here or 8 here, or I can end up with something like this, but reversing the 8 and the 10 because those 2 are considered unique. And yet, at the same time, they both meet the requirement of we have exactly a sequence of 7 numbers. Are we doing okay so far with this one? Now, the importance of this particular example is no one can precede a 1. Okay? That's important because when we go to the next one, it doesn't have that number constraint anymore. The more constraint you have, the better. But this one doesn't have that constraint anymore. So this time we start with a 2, ending with an 8. So once again, we have 3 numbers remaining, And we have to make sure, yep.
So we have a 1, 2, 3, 4, 5, 6, 7, 10, 9, 8.
Yes, we do.
8, 9.
Yep. Let's finish those two. Thank you. So 1, 2, 3, 4, 5, 6, 7, and then the 10. After the 10, I can choose whatever number. I can choose an 8 here, I can choose the 9 here, or I can reverse those two, and we'll still be okay. Thank you. Okay, the next one is starting with a 2. Now, this time it is a little bit different, okay? Because after the 8, I cannot have a 9, okay? But I can have a 10, I can also have a 1. Is that okay? As the very end, the last one, I cannot have a 1, I can have a 9 or a 10. So, okay, let's just work out all the possibilities here. So I'm going to pick a 10 here. Well, let's pick a 1 here first. Okay, so this is all kind of sorted in a particular way. So we start with a 1 here. We know the last one cannot be a 1 anymore, so we have two choices for these two positions. One is a 9, and one is a 10. And then we can flip the 10 and the 9, like that. And it will still not be able to complete the sequence. So now we work with the alternate, okay? So the other number that I can put right after the 8 is not a 9, so it has to be a 10. So after a 10 is taking up this position, technically speaking, the next one can be any number, but it really cannot be the case because the last number cannot be a 1. So if the last number cannot be a 1, it locks down the last number to be a 9, which means the only place a 1 can go is here. Do you see how, there's no symmetry here because I cannot reverse the 1 and the 9 to have a new sequence. Yep.
So if you put the 1 in the end instead of 9, then we're going to have a sequence of 9 numbers then, right? So it's going to go 1, 2, 3, 4, 5, 6,
Correct.
7, 8.
Which I don't want to double count because we already counted all of those
So
numbers.
that's why you're doing this.
Right.
Okay, got it.
Well, it's going to be 8 only, because if I reverse the 1 and the 9, in this case, then I have 1, 2, 3, 4, 5, 6, 7, 8, which is a sequence of 8 numbers only, which should be accounted for already in the previous count.
But we need the sequence of 7 numbers.
Yes, we want exactly 7 numbers in the sequence, not at least 7 numbers in the sequence.
Okay.
So this time there are only 3 choices, not 4 choices anymore. Okay. What if we start with a 3? Okay, so let's look at the 3 first. So 3. Okay, let's just take a look at these 3 cases. Are there any other ways to start with a 2 and end up with a sequence of exactly 7 numbers? I don't see any other ways. But you can also see, something is being asymmetric here. Okay, there are only 3 of these, but in the first case there are 4. If we start with a 3, then we have 3, 4, 5, 6, 7, 8, 9. Okay, that's a sequence of exactly 7 numbers. The only thing that cannot follow a 9 is a 10. So technically speaking, I can use an 8 or nope, I can use a 10, 1, 2. Okay, I can use a 1 or a 2 here. So I can use a 1. If I choose a 1 here, I have 2 cannot be the end. 2 cannot be here because otherwise 2 wraps around and connects with the 3. So that means 2 can only go here, which means the last number has got to be the 10. The 10 can only be the last one. Yep.
Where did the 2s go? You get rid of the 2s. The 3, right?
Say again.
So you have 4 possibilities, and then there are the 2, where the numbers start with 2.
You accidentally
Yeah.
deleted the ones that start with
Yeah.
2, 3, 4, 5.
So we have 1,
6,
1,
7, 8.
1, 1, and then
So the
2, 2,
sequence
2,
that starts with 2.
and then 3.
Oh, the entire sequence starting with 2. I think I just erased it.
Yeah.
Control Z, Control Z, 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 Z.
It looks so intentional.
There we go. Well, the whole thing is recorded. I mean, there's no way I can actually, delete it, right? I mean, the timeline, it cannot be distorted.
You could not post it on YouTube. That would do the trick.
Right. Yeah. So
We're
time
recording.
does not. So the time doesn't get registered. Yeah. Yep. But that's the cool thing of recording the whole thing is it's recorded. You can look at it prior to the deletion of this text here. I think that's how a Time Lord looks at time. They can because I think this is the difference. I know we are going to Doctor Who again. The rest of us, the non-Time Lords, are watching things on YouTube. So we are looking at something that is published, right? Time Lords are the ones doing the recording, and they have the capability of doing the editing. And okay, let's cross out this section before we publish it onto YouTube. And they can pull stuff out of YouTube too. So to the rest of us, reality changed. But to the Time Lords, hey, it's all the same stuff. I just pulled a few clips off of YouTube and extended one and changed the other one. So I think that's a good way to look at Doctor Who. Okay. End tag of a digression element. Okay, so 3, 4, 5, 6, 7, 8, 9. Okay, the next one cannot be a 10, can be a 1, right? The next one can be a 2, and then we have a 10 over here. Okay. What other ways can we arrange it? A 1 can go here. A 10 cannot go there anymore because if a 10 goes there, a 2 has to be there. So I can no longer start with a 1 with the part that is not in sequence. So I have to start with a 2 here. But now we have the 2 possible choices. Because if a 2 goes here, then the 2 remaining numbers, which is a 1 or a 10, none can continue the sequence on the other side. So now we can have a 1 here and a 10 as the end, or we can reverse the last 2 numbers, have a 10 here and a 1 as the last one. Okay? And we cannot end with a 10, so that accounts for all the possible cases. Okay, we start with a 4 when we only want a sequence of exactly 7 numbers. We can start with a 4. But the 4, starting with a 4 is going to be the same case as the first 4 cases, or in many ways it is going to be symmetric as these 4. So we'll go ahead and take a look at that one. 4, 5, 6, 7, 8, 9, 10. Okay. Well, any number can follow a 10 because 10 is already at the end. So I can put a 1 here. It will be fine. So I can have a 1, 3, 2 because I cannot have a 1, 2, 3. Otherwise, it continues the sequence on the other side, wrapping around. So this is the only one I can use, and starting with a 1. Then we have 4, 5, 6, 7, 8, 9, 10. And if I start with a 2, then I can have I cannot have a 3 as the end, so I can have a 2, 1, 3. Nope. I just said I cannot have a 3 at the end. 4, 5, 6, 7, 8, 9, 10. And if yep.
So in this exercise, we're looking for exactly 7,
Yes.
right? But are we doing that in our?
Are the arbitrary number?
No, in the homework assignment, we are looking for at least 7.
Okay.
But to get to at least 7, you can add up exactly 7, exactly 8, and exactly 9, which is also exactly 10. So you can use a sigma, a summation. If you can find out each one individually, you can just use a sigma and sum it up.
Okay, thank you.
Okay? All right, so the next one is going to be ending with a 3 here. Then I really get 2 choices because I can have a 1 first, or I can have a 2 first, and still be okay. Like that. So we end up with, in this case, we end up with 14 core permutations. And for each core permutation, we can rotate 10 positions, and we can also flip directions. So now we have 14 times 2 times 10, which is 280 additional cases. So you add these 280 cases to the 60 cases of when r equals to 8, or when we have sequence of exactly 8 numbers, and then plus the 20 of 9 and 10, then you have the total number of at least 7.
And why can't we start with 5?
Say again?
Why can't we start with 5?
Why can't we start with 5? Because if you start with 5, it will be a exact copy rotation-wise as something that is already here. Let's start with 5 and see what happens. Okay, so we'll start with the 5. 5, 6, 7, 8, 9. Oops. We've got a new line. 5, 6, 7, 8, 9, 10. But that's only 6 numbers.
We have to end with 4.
Hmm?
We have to end with 4.
What should be?
We have to end with a 4, correct. Okay, so if you end with a 4, then it becomes a rotation identity with one of the previous cases. No matter how you choose those 3 numbers, it will still be a rotational duplicate of one of the 14 cases that we have already worked on. Particularly, it will be, well, yeah, in this particular case, it's going to be a duplicate of the previous 4. Doesn't matter how you choose those 3 numbers, it will be an exact copy or rotational copy of one of the 4 assignments that we have just gone through earlier. Is that okay? So having the numbers here spelled out is definitely helpful, because then we can start to understand, oh, so why are there exactly 14 here? So the next question is, how do you come up with that number 14? How does that have anything to do with n and r? How does n and r affect this number? That becomes the next question. Yep.
Can you clarify what you mean by summing them up? Like you're summing the amounts of each variable that you get of each sequence and then adding that up?
So maybe a notation will be helpful. So okay. I think I used f already, so we'll use g. So let g rn equal to the frequency, or the number of outcomes where there are n slots in a circle. N numbers are assigned, and there is a sequence of numbers up to R numbers. Okay. So it's up to, because the other part can also be a sequence. I can illustrate what I mean by that. If you look at this one, we have a sequence of 7 here, but these 3 are actually a sequence as well. It's just not what we're looking for. Are we doing okay so far? Okay. So the G is a new notation. So this means, if I let FRN be basically the same thing, but not exactly. Okay, so we'll make a little modification after we paste. A sequence of numbers of at least R numbers. That's what your homework assignment is looking for. Okay, is at least. But how do you think these 2 functions relate to each other? Yep.
Complements, like based on the 1.
They're not complements, but there's the addition part. Yep.
So if you do G and then add up each G greater up to N.
You have to be careful, because n minus 1 and n are exactly the same. So you're trying to do the union. Okay, that's what we're trying to do, is to basically do the union. Let me see. What would be a better way to put this? How about this? Okay, I'll work on a very specific case here. So F 710 is the same as G710 plus G810 plus G910, but I don't want to add G1010 because G1010 is the same as G910, because what I'm really trying to do is to find the union of these sets. If two sets are exactly the same, the union would be exactly the same. So that's why I don't want to do this. This would be wrong because these two are really counting exactly the same permutations. So I don't want to do that. I only want to count unique permutations. So that's what I'm adding here. Is that okay? Yep.
So is G kind of like what we were doing with the exact, and then F is like what's in our whole?
Yeah.
Okay.
Yeah. Well, it's not exact either because we also have we can have shorter sequences. We can have sequences of less than R numbers. Because in this case, if you look at this particular case, we have a sequence of 7 to begin with, but we do have a sequence of 3 after that. Three, two, one is a sequence. It's just counting backwards. Yep.
So if we were looking for a sequence of 3, we would have 3 in that line to trim out. We'd have 4, 5, 6, 7, 8, 9.
But it would just meet that requirement.
It doesn't matter how many times it beats it, at least once.
Yeah. But the key is you don't want to double count permutations, and that's the difficult part.
Cool.
So what about 6? Okay, so now that we have worked up to R equals to 7 when n equals to 10, what about R equals to 6? Now R equals to 6 is going to have more cases, but that's only because we have more choices of the numbers in between the two ends. So I'll illustrate it using an example. 1, 2, 3, 4, 5, 6. That's a sequence of 6. The other 4 numbers cannot compete with the sequence of 6. They just cannot continue this particular sequence of 6. Nothing can continue as the last number, so it actually has a lot of freedom. But this number right next to 6 only can be anything other than 7. Okay, so it's got 3 choices. So let's pick 8 here. Now once we pick 8, we really can do all kinds of permutations with whatever is remaining, because there's no further restriction at this point. So that means, out of 7, 9, and 10, we really have 6 ways to do this. Okay, is that okay? Once we determine the first 6 numbers is 1 to 6, and then whatever number is right after that is an 8, we can just choose whatever we want, as the last 3 numbers. So that means, for this one, I want to multiply this by 6, which is 3 factorial, and then times 2, which accounts for the direction, and then times 10, which accounts for the rotations. What about this one? Ending with a 9. The same thing, okay? Because nothing can really finish the sequence anymore or extend the sequence. So same thing. And the next one is going to be the same thing. If we end with a 10, then there's no way we can actually extend the sequence any longer. So it is also doing exactly the same thing. All right. What if we start with a 2? Now that changes the thing. 2, 3, 4, 5, 6, 7. That's the sequence. So just like before, this number cannot be an, let's see, yep, it's correct. This number cannot be an 8, can only be a 9 or a 10. But the last number also has a restriction now. So now this time we have 2 restrictions as opposed to just 1. Because the last number cannot be a 1. So the last number can be, since I picked a 9 already, the last number can be a 10. That's it. Or 10 or 8, right? So 10 or 8. So we'll do the 8 first because we want everything to be sorted. So these two numbers in between can be any order. So that's 2 factorial. So it is still related to permutation because once you lock down the two ends, whatever you have in between is still a number of permutation. But this time we have a more, it's more limiting because this one now only has 2 permutations instead of 6. Once we lock down the two numbers, times 2 for the bidirectional thing, you know, clockwise versus counterclockwise, and 10 for the rotational. Okay, same 6 numbers. This time we'll pick 10 as the last one. Once we pick 10 as the last one, we can still pick a 8 here. We can also pick a 9 here. Okay, let's finish the other one first. You know, having the 9, we can also have a 10 here. Okay, so once we have 9 and 10. Then in between, you know, which is going to be the 8 and the 1, can be in any order. Yep.
Since there are 4 numbers in the first, the ones beginning with 1, right? There are 4 numbers we're not using. Why are we multiplying by 6?
Because the number right after the 6 is already determined. It cannot be a 7.
It's 3 factorial.
Yeah.
You can, yeah, go ahead.
I don't know if you answered it or not. I have a question. Does the end of and the beginning of the like a 1, for example, and the 1, if does count as a from the end to 1, does it count as an increase? You know how like you
10, 1, 2 is not a sequence of 3.
10, 1, and 1, 2 is not a sequence of 3. And is the end of the numbers?
Yes. Yeah, you cannot wrap around the number,
You
but the
cannot wrap
position
around
you
the
wrap
number.
around.
Okay, so and 1 is not a sequence.
Correct.
Thank you.
Okay, so getting back to this one, so we can have, is there any other way for me to use a 9 and, nope, that's it, it's right. If I fix, you know, the first 6 numbers to be 2 to 7, and then the next one as a 9, are there any other ways to arrange the numbers? Well, we already picked the 8 as the end. We know the 1 cannot be the end. So I think that accounts for all the cases where, you know, we lock down the 9 already. Okay, so now we lock down the 10. Once we lock down this 10 here, we know this one cannot be a 1. And we still have 8 to go, so 8 can be here. Times 2, times 2, times 10. 2, 3, 4, 5, 6, 7, 10. And once we pick 10 here, 9 can still go here. Okay. So 8, 9, 10, and then the 1. So because the only one that cannot be here is the 1. That's it. And I think I'm missing the one, you know, since I said, you know, I want everything to be sorted, I actually did not do it in a sorted way because 1 can be here. And once, you know, 1 is here, then we have all the choices that we can have. So in this case, we still want to multiply it by 6 times 2 times 10. So are there any questions? I mean, are you guys seeing, you know, how the numbers, you know, kind of work out? You know, it's a little bit tricky because the restriction has to do with what can continue the sequence. So you have to find out, okay, you know, what cannot continue the sequence, and you use that as a constraint to figure out the rest. And just to make sure that this part is done correctly, like that. Okay, any other ways to start with a 2? So the 7 cannot be followed by an 8. We have 9, 10, a 1 as a choice. So I think that really accounts for all the cases where you can start with a 2 and have a sequence of exactly 6. So then you do a 3 kind of the same way. do you think if you start with a 3, you will end up with the case kind of like the starting with a 1, or do you think it's going to be closer to when you start with a 3? Closer to when you start with a 2? It's going to be closer to when you start with a 2 because both ends can continue the sequence. That is the key. Okay? Is that okay? All right. So that means, so what this means is your answer most likely will end up, being something that has multiple summations or a nested summation. Because within just, counting exactly a sequence of 6, we already have, potentially a sigma notation. And then you have another sigma notation to add up all the g's to become your f's. But it gets even more complicated when r becomes a factor of n. Okay, let's think about it that way. When r equals 5, okay, things get it runs into a different direction, because this means well, r equals 5 is not that much of a problem. Let's pick r equals to 4, okay, because that one really illustrates the problem. Okay, so we can have 1, 2, 3, 4 as one sequence, and the next one has to break the sequence. So I can pick a 10 here, 6. I think either one will do the trick. And then we can have another sequence of 4 numbers, which is 5, 6, 7, 8. And then we can, I cannot do that, can I? I can put a 9 here and a 10 over here. That'll work. Okay? Now, there's a problem with this one, because it doesn't really have 10 rotational positions anymore. Now, it does have 10 rotational positions, but if you think about it, by the time we get to starting with 5, 6, 7, 8, 10, 1, 2, 3, 4, 9, now we have a problem. Because if you rotate the first one 5 slots, it becomes the second pattern. So with r being less than 1/2 of n, then you have to start to think about, what if we have 2 halves, or what if we have 3/3 or 4/4 that can be rotating and they look exactly the same after rotation?
You said everything less than 1/2 of n for situations like this.
Right. When you can have this type of problem, when you can have fragments where the rotation of the fragments can generate duplicate cases. So maybe for Tuesday, I just want you guys to turn in the answer where r is at least 1/2, because that's easier, okay? Because this is harder. This is a lot harder to account for.
Sorry, can you repeat that one more time?
Okay, so for next Tuesday, you only have to give me the solution where r is at least 1/2 of n. Because when r is below 1/2 of n, then you end up with problems like these. But it only happens when you can actually have a pattern repeating. So when n equals to 11, you don't have a problem. Because 11 it has nothing to do with even numbers versus odd. It has to do with whether it's a prime number or not. Because 11 is a prime number. With a prime number, there's no way you can have rotational duplicates. Is that making any sense? Huh? Only when n is prime. So I don't want you guys to worry about that part just yet. So just kind of focus on when r is at least 1/2. That will make it easier. Yep.
So I'm just thinking about the prime number thing with like n equals 5 for just to make it shorter. What do you mean that you can't
It means the way you count like this one, is not going to be a problem. okay, when n equals 5, okay, so let's think about when n equals 5. N equals 5, we can have, okay, what do you want to choose as r? Because r, the problem only happens when r is less than 1/2 of n. So,
3 then.
well, we only got one choice, right? Because when r equals 1, this is a trivial case. So this only matters when r is 2. Okay, so 1, 2 is a sequence. How do you organize the 3 other numbers to be not a sequence? You can have a 4, 3, 5, that would work, right?
Wait.
Huh?
Didn't you say only when r is greater than or equal to 1/2 of n?
Is what we have to turn it.
Less than or equal to.
Less than
r
or
is less than 1/2 of n in this case.
Less than or equal to.
Yeah.
Our homework is when.
Your homework is at least, yes. Your homework is at least, not exactly.
The homework is
At least.
but less than or equal to 1/2 n.
But you only, okay, your original homework is for the entire range of r, where r can go from 1 to n. But when r is less than 1/2 of n, the problem gets significantly more difficult to analyze. So I just want you guys to turn in the solution where r is greater than or equal to 1/2 of n.
So why are we
Okay.
looking at this?
Hmm?
So why are we looking at this example?
Just to see that rotation is not an issue when n is a prime number.
Oh, okay.
So we can also have 1, 2, can we start with a 5? Yeah, we can have a 5 and then a 3 and a 4 here. Okay. That's also an assignment that has no ending. Well, okay, this one does have 2 sequences of 2, okay, because 1, 2 is a sequence, and then 3, 4 is another sequence. Okay. So later on we can have a 3, 4, 1, 2, 5, and that becomes a duplicate. Okay, I guess that does happen. Whether it's prime or not, it's not important. Do you see how the multiply by 5 here doesn't work anymore? Because you end up with a duplicate. So is everybody clear, how, what you need to turn in on Tuesday? Okay. Yep. And you can use sigma notation, which means you can look at each individual case or break it up into multiple cases.
Cool.
Any other questions? Does this homework assignment still has anything to do with permutations?
Yes.
Absolutely. It's just that on top of permutations, there are extra constraints too. Why is this homework important?
Because you say you like us more than you actually do.
Well, but why are sequences important?
Proofs?
Proofs.
Recognizing patterns.
Recognizing patterns. But in computer science, whether something is in a sequence or not, why is that important? Especially in networking. Yep.
Well, it's not networking.
No, that's okay. Go ahead.
If you're looking for a signal from intelligence in space, and they have a sequence, that should tell you something. It's not background noise.
Aha. Okay, so if something indicates, sequencing, it is usually not because of random noise.
Correct.
Okay, so the representation of a sequence is a sign of intelligence. Well, I haven't thought of that one. Good one. Okay. Anything else? Anything related to networking that makes sequencing or sequences particularly important?
You told it to me already, so.
That's okay.
But
Go ahead.
when transferring data between 2 places, you gotta make sure that it was sent in the proper sequence of order, basically. So.
Exactly. So in TCP/IP, basically it is the job of TCP. When you transmit something through TCP, it should arrive in the same sequence as when you transmit it. Okay, but in between, it's broken up into packets or fragments. Those fragments, one fragment can go through routers ABC to get to the destination. The other fragment, the next fragment that is supposed to be in sequence, can go through router XYZ, which is an entirely different route. So these two routes can arrive at completely different times. So once you break up the transmission into all these fragments, each fragment can go through an entirely different route. So when they arrive, they can arrive out of sequence. So why is that? Why do we care? Because
the information is in sequence.
the information is supposed to be in sequence.
Yeah.
So the computer that is receiving all these fragments has to piece everything back together in sequence before it is presented to the program or the server that is supposed to process that information. Is that okay? So if everything is out of sequence, then the computer will need a huge buffer just to repiece all the things together, because everything can be out of sequence. You transmit your 2 gigabytes, and all 2 gigabytes are out of sequence. That would be a big problem, right? So you don't want that to happen. You want to find out, okay, what are the chances that something like that can possibly happen? Okay, so that's why, well, that's not exactly why we do this homework assignment, but it does explain why sequencing is actually important in computer science, because of transmission. Is that okay? Sort of? Yep.
So with the example you just gave, is that important to determine your buffer size, or is that
Yes.
important to determine the packet size?
Based on your buffer size, you can now determine, how many cases you can handle, or what is the worst case that you can possibly handle given a certain size of buffer. Because then at least you know what is the worst case scenario, and if you can calculate the actual chances of that happening, you can say, okay, this may happen, but the chances of this happening is 0.001%. Is that acceptable? If people say, yep, it's acceptable because it's not going to happen, then you're good. You're good to go. The chance, it will always, there's always that possibility. The question is, how slim is the chance, and is that acceptable or not? Okay. Any other questions? Most people look at computer science and go like, probabilities should not be important because everything is deterministic, right? Well, that's only with current generation of computers. Many of you, I think, I may not live to see that day, but some of you may live to see the day when computers are no longer deterministic and they become what? Probabilistic. But why do they become probabilistic? Quantum computing. Okay, so that really changes a lot of stuff that we already understand about computer science, because in quantum mechanics, what is the main difference between quantum mechanics versus traditional classical physics? Okay, quantum is one thing, okay, meaning things are in multiples of certain things, but that's one. Sorry?
Quantum entanglement with pieces that was.
But which piece connects to what we are talking about right now in quantum mechanics?
Sort of like certainty.
Certainty, distribution, probability distribution is the piece that kind of connects to this. Okay, now I'm not going to teach quantum physics, so do not tell your physics teacher that I'm teaching quantum physics in computer science. But ultimately, those two will be related in quantum computing.
Is that because of the uncertainty of where a particle will be in particular
Yep.
time?
It's the probability function. What is, if someone asks you to draw the orbit of an electron, what are you going to do?
Ask them which.
So I want you to draw the
model?
atom of a hydrogen. Or helium. Okay, helium is a noble gas. It can be on its own, so that's good, right?
All right.
So helium has got 2 neutrons and 2 protons. Okay, and it's got 2 electrons, right? So how do you draw those 2 electrons? The classical way to do that is
Perfect.
right? They're in orbit. They're kind of like satellites going around the nucleus. What's wrong with this picture?
They're constantly moving. It's too light.
It's an electron cloud.
It's an electron. It's an orbital, but an orbital, first of all, is not a track. It's not a 2-dimensional or 1-dimensional thing. It is a sphere. Okay, because this is the s orbital. The s orbital has a shape of a sphere. Okay, So now when you redraw this, which is also incorrect, okay, this part is also incorrect, I'll tell you why a little bit later. So now instead of drawing it on it's impossible to draw because this is now a sphere. The orbital is now a sphere around the nucleus. So it's pretty hard to draw. Okay, I know some of you have a VR or a, how do you call those things? Virtual reality goggle thing. So you can probably visualize, given you have one of those things, okay? So you can imagine there's a sphere that is extending out of the whiteboard, okay? So now that becomes the orbital, okay? But now the bigger question is, how can these two electrons be orbiting around a surface, the surface of a sphere?
Very quickly.
It cannot. There's no way to traverse it, okay? But as if this is not a problem enough, once you get to a heavier element, one that has more than 2 electrons, then you start to get into the p orbital, okay? The p orbital, well, it's not just a dome, okay? You have the nucleus, okay? So now we have a bigger nucleus here. You have the sphere, and then which is called the s orbital, and then the p orbital has one over here and the other one over here. It is one single orbital. So how does an electron go from here to here?
Spontaneous. Speed of light.
Or even
it's faster than the speed of light, right? So the electron will just disappear from here, sweep, reappear over here. It's a probability. Okay? In other words, the s orbital is not exactly the surface of a sphere. Okay? It's just a cloud that has the shape of a sphere. It is still a distribution function over 3D space.
It's like a clone. That's so fast.
It just randomly appears and disappears. Okay? But this picture is wrong. It is impossible to draw a nucleus, because the role of a neutron and a proton changes all the time. They're not statically assigned. Don't you guys like physics? I mean, yeah.
I mean, no.
But this stuff will become important because when we get to quantum computing, then the quantum phenomena will become important. So things are no longer deterministic. It's not like, okay, you flip a switch, it's on, or I flip it again, it is off. It doesn't work like that anymore. I can only imagine the excitement of future computer scientists when it gets to like quantum computing. Any other questions? Well, related to the homework assignment. No questions? Do you guys have to take quantum physics? No?
You take
Do they even offer that here?
441.
I don't know.
For undergraduate.
I mean, I know we went over that a little bit in chemistry for a little bit.
PChem has to go over that a little bit. Yes, physical chemistry has to go over the orbital a little bit. But I don't know how far they have to get into the quantum aspect.
We spoke about quantum, some quantum entanglement and stuff like that.
Oh, okay, that's good. That is good. Because even Einstein, could not accept quantum physics. He said, God does not throw dice. And then he just flat out rejected, quantum physics. He just said, nope, it's
Who
not
is he
possible.
to say what God does and does not do?
Well, because at the time, people already recognized him as a really smart person.
Talks with the dude.
So, any other questions related to the homework assignment? Is it all good? Okay. So once again, if you have not written a program to generate the patterns and then test it and then do the counting, do that because it will be very helpful because you can actually see the patterns, okay? Once we get to when n is 10 and r is 6, the number of items is too much, so I have to kind of generalize and give you just a pattern. But if you see the pattern, it will really help you understand, okay, there has to be a pattern. There has to be a way to do the counting without having to generate all the patterns and then actually count the number of patterns that meet the requirement. Okay? Yep.
Even if we
Yep, include everything. Your form will most likely will include like a nested summation, something like this. So just try to simplify and abstract it as much as you can. Okay. Yep.
Can we write a piecewise defined function for our closed form?
Piecewise. What do you mean by piecewise?
For example, if R is greater than this, then
Okay,
this
sure.
is R than that.
Just try to push it as much as you can. Just push it into as general as you can. Give me the form that is as general as you possibly can make it.
Summation. Everything can do if R equals and R is less.
Yeah, so within here you can still have conditions.
Have at least one condition point bigger.
With ternary operators.
Yep. So I will give you a preview of, okay, since we spent kind of a lot of time talking about the homework assignment, I still want to give you a preview of where we are going next. So we are going to be done with this. We will move on to recursion. And the recursion slide is kind of interesting because it talks about not really just recursion itself, but it talks about recurrence relations. In other words, they talk about algorithms that are recursive, and there's a thing called the Master Theorem, which I think is really kind of like an awkward name for a theorem. But you can find it in Wikipedia, which means it has got to be important as well. The Master Theorem is basically a way to compute the big O notation of a particular recursive algorithm, but based on very general patterns of the recursive algorithm itself. Okay, so that's why it's useful. So before we get into the Master Theorem, I definitely will have to go through the big O notation because not everybody was exposed to the big O notation when they went through CISP 300. So we'll go through the big O notation first, okay, to make sure people understand what is the big O and the big omega notation. And then we'll proceed to talk about the analysis of time complexity using the Master Theorem. So if you haven't done so already, this is where we will be. So go ahead and read ahead of me. Are there any questions? How many people know? Go ahead, sorry.
I had a quick question. What was the difference between like omega and the cardinality of omega?
Oh, that omega is different. The big omega notation has to do, one is the upper bound and the other one is the lower bound of the estimate of the time complexity of an algorithm.
Okay, and then for the homework.
For the homework?
For the homework part of the question was find omega and find the cardinality of omega. But I thought they were the same.
Omega is the set. So omega itself is the set of all possible outcomes. And then the cardinality of omega is what you use as the denominator to find the chances.
So are we expected to enumerate the whole set?
Say again?
Or for our homework, are we expected to enumerate the whole set or just get the cardinality?
Just do the count. Well, you will need that to do the chances. So you already, well, we talked about this several times already. So we kind of know the omega or the cardinality of omega for a particular n. So that's all you need. It's just the cardinality. You don't need to enumerate all the elements in omega. Okay. Any other questions? Just a quick survey because I still have 5 minutes left. How many people know already what is the big O notation in the context of algorithm time complexity? Okay, so we have about half of the class knowing it, and then the other half, well, maybe 1/3 not knowing it. So I'll kind of go through it really quickly, in the next class of what is the big O notation, and then we'll proceed and talk about the Master Theorem. Is that okay? All right. How many people like recursive algorithms?
I mean, I haven't done
Interesting to me.
Hard to
You
read.
can turn anything into recursive and turn anything that is recursive into iterations. It's just a matter of which way is more convenient and which way is more efficient. So that's really the matter.
Which way keeps you from ripping
Just
up
wondering, how many recursive calls have you made personally in your career? Like how deep have you gone into a recursive call? Like you've called it like 9 times?
Usually not very deep. Yep.
I mean, if you get too deep, it gets very crazy stack.
Well, recursion is interesting, but when people how should I put it? There are two aspects to auto local variables. Okay, now this is C and C++ concept, so I expect everybody to know it. In C and C++, there are two types of local variables. Okay, if you don't say anything, everything is automatically auto, which means it is stack-based. It's specific to an invocation. But you can also add the word static in front of a local variable. Then all invocations share the same local variable.
You just gotta be careful about when you go to call it again for a separate instance, it'll retain the values unless
Right.
you
So
wipe it.
most people think this is only dangerous when you have recursive algorithms. Because in the recursive algorithm, the algorithm in the subroutine calls itself, so if you have a static local variable, then the same thing is going to be used again, which means a later invocation will trash the value that is already put in there by an earlier invocation that is still active but is suspended. Okay? But that really is not the case. Static is bad in general. It's not just bad for recursive subroutines, it's also bad for any other subroutines. And I'll give you one reason why that is the case. It has to do with interrupts. In other words, subroutines, quote unquote, called by hardware. Because those subroutines can end up calling a subroutine that it is interrupting. So if the subroutine is using static, then multi-threading is not going to work either, because all the threads of the same process is going to trash exactly the same location if they so happen to call the same subroutine. So that's why this is a bad idea in subroutines. I really personally do not see any reason why people should do this. Yep.
What if it's a static const?
Huh?
What if it's a static const?
Then it's just a const. Yep.
Then
It's to be okay.
Just a const.
Yep. So constant would be okay to be static, but you need it to be local to a subroutine if it's a constant.
I used static consts in my program for this project. So
Inside the subroutine or just
no,
global?
as the size of the array.
Okay.
So it's fine.
Yeah. I think static const are the only reason why people should use global variables. There should be no other reasons, or very few other reasons to use global variables. Yeah. All right. Well, I'm done with the cisp440.
Well, unless you're testing XYZ in a C++ environment.
Say again?
Unless you're testing X